Swayamprabha. Digital India. Educated India.
Greetings to you all. We are now on to module 4 of this course. In this week, we have seen so far finite differential scheme and how to obtain forward backward central differential scheme for first derivative, and same by to get higher order finite difference formula. In today's class, we will particularly find out how to get derivation for non-uniform mesh and how to get mixed derivative and how to obtain finite difference formula for higher derivatives. So, this is necessary in the sense you do not have always an option of getting a uniform mesh throughout the domain. You want to have finer mesh at some location and coarser mesh at some other location. So, in such situation you need to have a formula derived based on non-uniform spacing mesh, and this graphically shown here a situation with function and I is a point of interest and I plus 1 and I plus 2. Unlike other case, distance between I plus 1 and I is delta x, and distance between I plus 2 and I plus 1 is alpha times delta x. And if you look from I plus 2 is at a distance of 1 plus alpha delta x. So, we follow the same procedure, write down Taylor series expansion formula, but now with alpha as a coefficient for delta x. So, that is also given here. This is already known, f of x plus delta x as f of x plus delta x and so on, equation 1. Now, the new difference here is for f of for the second point, which is alpha delta x between I plus 1 and I plus 2, or with respect to I it is at a distance of 1 plus alpha delta x. So, if you write the expansion for the function at I with respect to I plus 2, then you get formula written here f of x plus 1 plus alpha delta x as this. The only difference between equation 1 and equation 2 is delta x is replaced by 1 plus alpha delta x. Everywhere also it is delta x squared, for example, is replaced by 1 plus alpha squared and delta x squared and so on. So, as we did in previous case, here also we are interested only the first derivative. So, we consider only the first term and follow some arithmetic operation to get derivative, and if you consider higher term, then you get corresponding either higher order derivatives or higher derivatives difference formula. This equation 1 and this equation 2, by multiply equation 1 by 1 plus alpha and add it to equation 2, and we get equation in this form f of I plus 2 minus 1 plus alpha f of I plus 1 plus alpha times f of I equal to this, and we are interested in the second derivative here. So, we retain that term, remaining terms are brought to the other side. So, that is given here as f of I plus 2 minus f 1 plus alpha f of I plus 1 plus alpha f of I, and this coefficient is brought to the denominator, and this is of order delta x cube, and if you divide by delta x square, then you get of order delta x. So, we obtain second derivative forward difference formula for non-uniform mesh, and this is of order delta x. Now, if you substitute this expression into the equation 1, which is basically equation for forward difference, after simplification we get first derivative forward difference formula with non-uniform spacing, and that is alpha is here. So, this is of order del x squared. Now, you also have mixed derivative, that means derivatives with two independent variables. So, for example, dou squared u by dou x and dou y. In this case, u is a function of x and y. So, there should be a procedure to obtain finite difference formula for this mixed derivative also. Now, we are going to see how to get derivatives with the two variables, otherwise it is called mixed derivative. Again, function f is dependent on x and y. So, we do the expansion, Taylor series expansion with f of x plus delta x and y plus delta y, and we see here the Taylor series expansion formula written f of x and y del x dou f by dou x with the new term here for the other direction del y dou f by dou y. So, this comes as a pair. Now, again next term del x squared by 2 factorial dou squared f by dou x squared del y squared by 2 factorial dou squared f by dou y squared and other term. So, we are actually interested to find out dou squared f by dou x dou y. This is what is called mixed derivative or derivative in two direction. So, if you write in I form and j form, so I is for x direction and j for y direction, and it is written here as del f of I plus 1 and j plus 1 corresponding to f of x plus delta x and y plus delta y, and we are actually interested in dou squared f by dou x and dou y. Now, we have written this expression for f considering I plus 1 and j plus 1. We can repeat this for different combination of I and j, and that is what is given here, f of I minus 1 j minus 1, f of I plus 1 j minus 1 and f I minus 1 j plus 1. So, in all the three expression here and one expression in the previous slide, we have a mixed derivative term dou squared f dou x dou y, and so we have 4 equations where the mixed derivative is appearing. So, we do simple arithmetic, add all of them and take an average, and you get finally expression for mixed derivative as shown here. So, dou squared f by dou x dou y, which is evaluated at I comma j with function values considered from neighboring points, that is f of I plus 1 j plus 1, I plus 1 j minus 1, I minus 1 j plus 1, I minus 1 j minus 1 and 4 times del x and del y, and this is of order del x squared as well as del y squared. So, it is second order accurate in both x direction as well as y direction. Once again, we have written only for a uniform mesh. It is possible to obtain mixed derivative expression also for non-uniform mesh and for any combination of non-uniform mesh, in the sense it may be uniform in x direction, non-uniform in y direction, vice versa also is true, and it may be non-uniform in one way in x direction and non-uniform in another way in y direction. So, any possible combination of mesh is arrangement is possible, and it is possible to obtain derivative for any arrangement of mesh. The last slide we had seen how to obtain different scheme for the mixed derivative. I rewrite that formula here again, dou square f by dou x dou y equal to f at I plus 1 j plus 1 minus f at I plus 1 j minus 1 minus f I minus 1 j plus 1 plus f I minus 1 j minus 1 divided by 4 delta x delta y, and this is of the order delta x squared and delta y squared. Now, if we look at the stencil, what is shown here is graphical representation. The blue color is a point of interest, the nodal location x of I and y of j, and it is influenced by neighboring nodes as shown here. For example, this node is at x I plus 1 and y j plus 1, this node x I plus 1 y j minus 1, and here it is x I minus 1 y j minus 1, and here it is y j plus 1 x I minus 1. So, it looks for this mesh arrangement which is uniformly spaced in x direction and uniformly spaced in y direction, and also del x equal to del y. That is why you get a equal, it appears as if the mixed derivative evaluated at this point has a equal weightage from surrounding mesh points. It may not be so in the case of non-uniform mesh. So, we have obtained derivatives, first derivative, second derivative, mixed derivative, uniform mesh and non-uniform mesh. We have to see one more expression or one more expression for one more term, that is higher derivatives. So, we extend the procedure, we got Taylor series expansion f of x plus delta x, f of x plus 2 delta x. Now, we do one more by considering one more point, that is x plus 3 delta x. So, all the three expressions are given here as equation 1, 2 and equation 3. Of course, now you understand the pattern, how to write Taylor series expansion in any direction forward or backward by considering one nodal point, two nodal point or three nodal points, also for uniform mesh or non-uniform mesh. By this time you are very much familiar and you are able to recognize each term, each expression in each term. So, equation 1 is for delta x and equation 2 is for 2 delta x and equation 3 for 3 delta x. What is our goal? Our goal is to get higher derivatives. So, we have seen up to first derivative dou f by dou x, second derivative dou squared f by dou x squared. Now, we are interested to get third derivative as an example of higher derivative. So, that is why we have considered 3 expression. So, multiply equation 1 by 3 and subtract from equation 3. So, we are going to do 2 small arithmetic operation, equation 1 by 3 and equation subtracted from equation 3. So, if you do that, we get expression like this, 3 times f of x plus delta x minus f of x plus 3 delta x, and on the left hand side, on the right hand side you have a remaining term. We name this as equation 4. Then one more small operation, multiply equation 1 by 2 and subtract it from 2. Then we get one more equation that is shown here, f of x plus 2 delta x minus 2 times f of x plus delta x on the left hand side, on the right hand side minus f of x and remaining term, and we name this equation as number 5. Now, between 4 and 5 again we have to do small arithmetic operation. We are only interested in third derivative term, that is dou cube of f by dou x cube, and that is appearing in both equation 4 and 5. this second derivative term appearing in equation 4 and 5 needs to be removed. So, we do a small arithmetic operation solving the above two equation, that is multiply equation 5 by 3 and add it to equation 4, because the second derivative term that is here has coefficient 1. So, if you multiply this by 3 and if you add with this corresponding term here, then you can observe that this term as well as this term gets cancelled. That is why it is equation is 5 is multiplied by 3 and you add it to 4. So, you get dou cube f by dou x cube as f of x plus 3 delta x minus 3 times f of x plus 2 delta x plus 3 times f of x plus delta x by dou x cube, and this is of order delta x. So, in this class what we have done how to obtain finite difference procedure on a non-uniform mesh and how to obtain finite difference procedure or finite difference formula for mixed derivative, that is derivative in two direction. And third important subject was how to obtain finite difference formula for higher derivative. As an sample we took the third derivative dou cube f by dou x cube. In next class we will see how to obtain finite difference formula by other procedure, that is we have seen getting all finite difference formula only from Taylor series expansion. There are also other procedure available and we are going to see one such procedure in next class. Thank you.